Okay, is this good? All right, good morning. I'd like to pick it up where we left yesterday. So remember that we were bounding uniform deviations between probabilities and relative frequencies. And we saw that this can be upper bounded by twice the expected value of this conditional Rademacher average, which has a kind of natural interpretation of measuring the richness of the class, of this class of sets. Right? If this class is big, then I will be able to correlate the sequence of these indicator functions with a completely random sequence in a very well, and then this will be a large number. Okay? And otherwise, if the class is small, then all of these things are zero mean random variable with typical deviations of about square root of n, right? So if this class is not too big, then this should be of the order of square root of n, well, divided by n, so this should be of the order of 1 over square root of n. So this is the kind of the range that we can expect. If this class is small, then we should have something, this Rn should behave something like 1 over root n. And if the class is very large, then it can be much bigger. Particularly if this class is huge, for example, it contains all possible sets, then this will be always 1, right? Because I will be able to perfectly match these indicator functions. I will always be able to find one set which matches the random sequence. Okay, so this is our upper bound, and we showed here that this quantity Rn is very well concentrated. This is the slide that contains the mistake, because here I should write n times Rn and n times Rn everywhere. But they asked me not to correct it, so that in the video it's consistent. Okay, so these inequalities for n times Rn, and this shows that in fact this expected value can be bounded by Rn itself, and we can measure that because this is a data-dependent quantity. Okay? And this is what we like in machine learning. We want to bound the performance, the expected performance of our algorithm in a data-dependent way. We can look at the data, we can calculate this quantity, and since we know that it's always close to its expected value, its value will be a good approximation for this. Okay? So these are the typical statistical or learning theoretical applications of concentration inequalities. Right? Now that I have come so far about talking about Rademacher averages and maximum deviations of relative frequencies from probabilities, I can't resist to prove actually the Vapnik-Chervoneck's theorem, which is now just one step away. So this S is the so-called shatter coefficient, or the log of this is sometimes called the Vapnik-Chervoneck's entropy. So we just look at our data, fix our data, and count how many different subsets from our class generate. Okay, so we have our data points here, and now we have our class of sets, and this is one set, maybe this is another set. These two sets intersect with our data points on the same 2 points. Okay, so these will count as one. So we just count how many different subsets of this we can get out. So that there are this S x1 n a is clearly always less than or equal to 2 to the n, because for n points we can have at most 2 to the n subsets. Okay, so this is called the shatter coefficient. If the class is small, then this will typically be much smaller. Okay? For example, you can think about half spaces. If our class is of half spaces, then you can prove that this S is less than something like, I think it's n plus 1 to the d or something like that, where d is the dimension. Okay, so you can prove bounds like that, which are much smaller than this. Okay? If you're familiar with Vapnik-Chervoneck's theory, then you know exactly what this is about. Now, if you look at the Rademacher average, right? The conditional Rademacher average, then here the x's are fixed. And the expected values with respect to the epsilons. Right? So this supremum is actually, even if our set is an infinite set, this is over finitely many different sets. Right? Because we have at most as many different sets in that, different sums as the number of sets here. Okay? So we have now the expected value of a maximum of Sn guys, Sn random variables, and these random variables are these sums of plus minus ones times something. But these are sub-Gaussian, right? Because we showed that was Hövding's inequality. So we have now a maximum of this many sub-Gaussian random variables, and we look at the expected value. Well, we know how to bound this. We know that the expected value is less than the square root of the log of the number of random variables divided by 2n. Remember this bound? Let me show you again. I'm using this bound. Right? We have the expected value of the maximum of capital N sub-Gaussian random variables, then we have this upper bound. Okay? But this is what we have now. We have this many random variables. When the data are fixed, they are all sub-Gaussian, so I can use this inequality. And that's this bound. Okay? This is for the conditional Rademacher. In particular, the expected value of the maximum deviation is less than twice the expected value of the conditional Rademacher average, which is this guy. Okay? Remember, this is a random variable. The number of sets that we can generate is depends on our actual data. Okay? So this is somehow the data-based complexity of the class, the data-dependent complexity of the class. This is a random variable, and our upper bound is in terms of the expected value of this. Okay? Many times, for example, when we have half spaces, we can upper bound this in a non-data dependent manner. Okay? So that's what Vapnik and Chervonenkis did in the original days. Okay? But this is actually, we get it for free, that we get the expected value of the log, square root of the log of this number. Okay? Now, this bound, and I'm not going to go in the combinatorics of this, but if you're familiar with Vapnik-Chervonenkis theory, then you may know that this shadow coefficient can always be upper bounded by n plus 1 to a combinatorial dimension, which is called the VC dimension, the Vapnik-Chervonenkis dimension. What's the Vapnik-Chervonenkis dimension? It's the largest value of n such that this number equals 2 to the n. Okay? So we start putting points down one by one, and when I have put down 1 point, if I have a set which in my collection that contains this, and I have a set that doesn't contain this, then S equals 2 to the 1, so the VC dimension is greater than that. Now if I have 2 points, then I may or may not have 4 different sets that give all my combinations. If I don't, then I have found the VC dimension. Okay? If it's still 2 to the n, then I don't know what the VC dimension is, and we keep going. Okay? So the VC dimension is the largest number n such that this guy equals 2 to the n. Okay? So the largest number such that there exist n points that can be shattered. We say that these n points are shattered if I can pick out all 2 to the n possible subsets of this using my class of sets. Okay? And this depends on the data, of course, again, okay? Because I'm using these points. So the shadow coefficient can be upper bounded by this combinatorial dimension times log n. All right? This is again a random variable. Right? The VC dimension, if I write it like this, it depends on my data. It is a random variable. So is it concentrated? It is. Why is it concentrated? This is a very nice little fact. So the random VC dimension on n points, this guy, is, so I put down n points here, and I look at all possible subsets of size V. And if I can find a subset of size V such that this subset is shattered, then I say the VC dimension is at least V. So the random VC dimension is the size of the largest subset of my point set that can be shattered. So that all 2 to the that many points can be picked out. Okay? That's the definition of this number, the random VC dimension. Okay? So for a given point set, I look at what's the largest subset of this point set such that I can, for example, in this case, I can find 8 sets that give me all the combinations. Okay? All right, so why is this concentrated? Well, I will use the Efron-Stein inequality. What does the Efron-Stein inequality say? Remember that if I have a random variable v, and I can look at any other function which only depends on n minus 1 points when I take out the ith guy. Okay? So let me define v sub I as the VC dimension on the rest of the points. Okay? Good. So what can happen with the VC dimension if I delete 1 point? Well, 2 different things can happen. Let's look at the set of points that witnesses the value of v. Okay? What does it mean? It witnesses the value of v that take a subset of points which is maximal subset, a subset of maximal size, and it can be shattered. All 2 to this many points can be taken. Okay? So this subset witnesses the value of v. Now, if this is xi, if I delete this point, which is not in this set, then nothing happens. Then difference will be 0. If I delete one of these points in the maximal set, then 2 things can happen. Either there's another maximal set, and then this difference is 0, or if not, then this can decrease by at most 1. So this guy is always when I take out 1 point, the VC dimension on the rest of the points can only decrease, and it can never decrease by more than 1. And if I take the sum of these differences, then this can decrease how many times? Well, at most v times. Okay? Because whenever I delete a point which is not in this maximum shattered subset, then nothing happens. So the number of changes is at most v. Okay? So these 2 things show this is what we call a self-bounding function. Okay? When we have a random variable that has these 2 properties. Remember, we have already seen an example of a self-bounding function, which was n times the Rademacher average. It had exactly the same kind of property. And we showed that the Efron-Stein inequality, in this case, shows that the variance of v is then less than or equal to the expected value. This is the Efron-Stein inequality of the sum of v minus vi squared. But v minus vi squared is less than v minus vi, so this thing is less than the expected value of v. So the variance of this random VC dimension is always less than the expected value of the VC dimension. So this is another example of a complicated random variable that's always concentrated. It's always concentrated because the typical deviations are of the order of the square root of the expected value. So if the expected value is large, then the typical variations are much, much smaller. These are Vapnik and Chervonenkis. I don't have a better picture of Chervonenkis. If you have one, send it to me. So they were the one in the late 60s. They already did this kind of stuff, and the learning theory people picked it up about 20 years later. All right. So maybe I should say just one more word about self-bounding functions here. So there are actually many examples of random variables that satisfy this type of inequalities. So these are the so-called self-bounding functions. And one class of such functions is what we call configuration functions. And roughly, configuration functions are like the random VC dimension. So suppose that we have n random variables, and the function that we are interested in is the largest subset that has some kind of property, some kind of hereditary property. So whenever we have something like this, then these type of bounds can be verified very easily. Let me show you one example, and I think then you will see what I'm talking about. So take n random variables uniform between 0 and 1. So let me just. So here, this is 0 and this is 1, and I pick a random guy everywhere. Okay. Now, so this is x1, x2, and xn, and I pick them uniformly. Now I'm interested in the length of the longest monotone subsequence. So this and this guy, this is a monotone subsequence because it increases. But this is not the longest because I can pick one which contains this, this, and this. So the length of the longest monotone subsequence in this example, that's my random variable. Okay? So Ln is the length of the longest monotone subsequence. Okay. So it's a famous theorem that says that the expected value of Ln is something like twice the square root of n. Okay. There are various ways of proving this. But now we can ask how concentrated are these? Well, we can use our configuration function bounds. Why? Because we have exactly the same phenomenon with the VC dimension. I can define Lni as the length of the longest subsequence when I delete xi. If I delete this point, then I can still define my random variable. And now we can look at the difference between Ln and Lni. So what can happen to the length of the longest subsequence if I delete this guy? Well, it can only decrease. Right? It can never be longer because I have less points. By how much can it decrease? For sure, not more than 1. Right? And it can only decrease if the random variable I delete is actually in the longest subsequence. Okay? I fixed there may be many longest subsequences. So for example, I may have another guy here. So this is another longest subsequence. Doesn't matter. I fix one of them. And for sure, if I delete any point which is not in this subsequence, then I still have a subsequence which has the same length, the amount of subsequence which has the same length. So the sum of these guys is less than the value of the function. This is another self-bounding function. And the Efronstein inequality tells us that the variance of this guy is less than the expected value. Which means that typical deviations are at most of the order of n to the 1/4. Right? Because it's going to be the square root of the expected value. Which is very small compared to the expected value. in fact, this is not the sharpest possible bound, but it's the simplest that gives something very interesting. In fact, you can prove that the typical deviations are not of the order of n to the 1/4, but n to the order of 1/6. But that is a very difficult result. Okay? But many times, using Efron-Stein, you actually get something that's close to optimal or optimal, but it's always simple to use. Okay? I have no idea how sharp this is in general in the case of VC dimension, but we get something which is very useful and nice. All right. Any questions so far? All right. So up to now, we have only been interested in the variance. Well, at the beginning, I showed you some exponential bounds for sums of independent random variables, and we argued that those are much more useful in many situations. Now, we would like to say something about exponential concentration inequalities for functions, for arbitrary functions of independent random variables. So next I will, basically in the rest of the course, I will be interested in doing something sharper than Efron-Stein. Efron-Stein is very simple and very easy to use, but it only tells us something about the variance. And many times we need something much sharper. Okay? So let's see what we can do. So again, the setup is the same as in the case of in the Efron-Stein setting. So we have n independent random variables. They take values in some space. It doesn't matter what's set. And we have a function of n variables. Okay? And this defines us a real valued random variable. And we want to know how close this random variable is to its expected value. Okay? So the first idea is to try the Doob martingale representation, which was very useful. This is how we got the Efron-Stein inequality. So let's see if we can say something. Okay? So we write z minus ez as the sum of these martingale differences. So remember, E sub I is the conditional expectation of z when we fix x1, xi. It's here, the definition. Okay? So we can write z minus ez as this telescopic sum, and the Efron-Stein inequality we got by observing that these guys are uncorrelated. They're not independent, but they are uncorrelated. Good. Now, if we want to mimic the proof of Chernoff bounds, then we might be interested in bounding the moment-generating function. Right? So remember that the idea of Chernoff bounds was that we said that the probability that a random variable exceeds its mean by more than t, well, we wrote this as the probability that an e to the lambda, when lambda is a positive number, then this is an increasing function, so z minus ez greater than e to the lambda t. And now we used Markov's inequality. This is less than the expected value of this non-negative random variable, e to the lambda z minus ez, divided by e to the lambda t. And then we went on and we used independence. When z is a sum, then we could use independence because we could take the sum outside of the expected value by independence, and then we could bound just the individual terms in the moment-generating function, and that's how we got Milgren's inequality, for example. Okay? So we can try to look at what happens here. All right. And we can actually do something under some assumptions. And these assumptions is that if the martingale differences are bounded. Okay? So suppose that our function is such that this guy is always bounded by a constant. Okay? Almost surely. So there's no way it can be larger than some number, let's say c. or C sub I. Okay? So suppose that these martingale differences are bounded. And we will see that there are, in fact, interesting cases when this happens. Okay. So then what can we do? So the moment generating function that we're interested in, well, we wrote z minus ez as the sum of these martingale differences. And now I write this expectation as the expected value of the conditional expectation given x1 to xn. Actually, this should be n minus 1. Xn to x minus 1. So I'm only taking here inside the expected value with respect to the last guy. Okay? But then, all this term is a constant. So this e sub n minus 1 can go inside, right? So if I take the expected value of this conditional expectation, then this term, because the exponential function converts the sum into a product, then I can, and this part of the product doesn't, it's determined by x1, xn minus 1. This is the function of the first n minus 1 guys. It can come outside. This is a constant with respect to this guy. Okay? This is a conditional expectation. This is en minus 1. Okay. Good. But now, what do I have here? Delta n, that's a bounded random variable, and this is just the moment generating function of a bounded random variable. And that was Hövding's inequality. Remember, Hövding's inequality tells us that if we have the moment generating function of a random variable that takes values in a bounded set is less than e to the lambda squared divided by, well, we put 8 when x took its value in an interval of length 1. Well, here the length of the interval is 2c sub I, so we get this guy. All right? This is just rescaling Hövding's inequality. So by Hövding's inequality, I can upper bound this by this constant times this guy. All right? But this is a constant, so it comes outside, and what remains inside has exactly the same form as before, so we can recurse. We can repeat this argument. We repeat this argument n times, and we end up with the product of these terms, which is this guy. Okay? This is a famous inequality. This is called the Azuma-Hövding inequality, or Azuma's inequality. So what this says is that if I have a sum of bounded martingale differences, okay, if I can express z minus ez as sum of martingale differences that are bounded like this, then the moment generating function can be bounded exactly as in Hövding's inequality. So for free, when we have this boundedness assumption, Hövding's inequality generalizes from sums of independent random variables to sums of martingale differences. Okay? We just have to do the argument one by one. Okay? All right. Good. So this is tremendously helpful. And this not only for studying concentration of functions of independent random variables, but many times we can just study martingales of bounded increments. Okay? Now, in our case, when our martingale differences were defined like this, you can see that if our function has the bounded differences property, so what does the bounded differences property say? So if our function f is such that if I change one variable but keeping all the others fixed, so if I change the ith variable to something else, but I keep all the others untouched, then if the function is such that the value of the function cannot change by more than c sub I, this is the bounded differences property, then one can easily see that these martingale differences will be actually bounded. Right? Because here I take the expected value with respect when I fix x1 to xi, and here I only fix x1 to xi minus 1, so the only differences are in the ith variable, so this is immediate. Okay? That if my function satisfies this kind of property, that by changing one variable, the value of one variable, the value of the function cannot change by too much, then these martingale differences will be bounded. And I can use the Hövding-Gazuno inequality. And so that's what's written here. This is what we get. This is the famous bounded differences inequality. So if I have a function that has this property, that by changing one variable, the value of the function cannot change by much, then I have an exact analog of Hövding's inequality. Okay. So for example, if f is a sum of bounded random variables, then this is, for that special case, this difference will be just the bound on the ith term. If f is a sum, then this difference is just the value of the ith term minus this guy. Okay. And then we exactly recover Hövding's inequality in that case. Exactly. So this shows that, again, it's the same kind of phenomenon that we saw with the F-from-Stein inequality, that among somehow all functions, sums have this extreme property. Okay. Sums are somehow the least concentrated. And for any function, and this is a tremendous, yes?
So for which values of Ci, is it stronger than Hövding's inequality?
It's never stronger. It's more general. So we recovered this. So for the special case when f is a sum, we recover exactly Hövding's inequality. But this is for arbitrary functions. And this is tremendously useful. So when this inequality was put forward in late 70s, early 80s, this is called McDiarmid's inequality, because Colin McDiarmid wrote a very nice survey, I think in '89, of lots of consequences in the theory of random graphs of this simple inequality and related inequalities. Nice shirt. When people realize this inequality, it caused a big revolution, because it's so easy to use. There are many situations where you have a really complicated function, but it's stable. It's easy to see what happens when you change one variable. If you do it in a clever way, then you can get a lot of mileage out of it. Okay? So the bounded differences inequality is something to try always. Okay? Just like the F-from-Stein. It's almost as easy to use as F-from-Stein. Okay, so here's one example of how this is useful. Okay? We can prove Hövding inequality in a Hilbert space. Okay? So take vector-valued random variables, and this can be an infinite-dimensional vector space. Suppose that we are in a Hilbert space. Okay? As learning theorists, you must like Hilbert spaces. Okay? So we have n independent random functions, if you wish. Okay? So Hilbert space values random variables, and suppose that they are bounded in the sense that the norm of each of them is bounded by C half. Okay? And let V be this quantity, n times this constant C squared divided by 4. Okay? Then we can look, so the expected value of this random variable is 0. Okay? So now we can look at the norm of the sum. Okay? How far this can be from T. And this inequality tells us that, well, this guy V is about of the order of n. So here we have T minus root n squared so this will be small when T is larger than root n. Okay? So if T is much larger than root n, then this guy is going to be very small. So this is an analog of Hövding's inequality. We have this sub-Gaussian decrease. And this is in infinite dimensions. Okay? So how do we prove such a thing? Easy. It's basically a trivial application of the bounded differences inequality. Why? Because this norm has the bounded differences property. If I change one variable, then the norm, because of the triangle inequality, cannot change by more than this guy. Okay, by C. Is this clear? If I change just only one term in that sum, then the norm cannot change by more than the maximum range of this variable, well, twice. Okay? So this means that the probability that this guy is greater than t, well, I can rewrite this as the probability is this guy differs from its expected value by more than t minus its expected value. Okay? And now I can use the bounded differences inequality. Right? Because the bounded differences inequality tells me that if I have a function of bounded differences with this property, then the probability that it deviates from its expected value by more than some constant is less than e to the minus this constant squared divided by twice, and we have the sum of the c squared. Yeah. So up to here, I only used the bounded differences inequality, and now it's just a very simple matter to check that this guy here, this expected value, is less than the square root of v, and this follows simply because well, this is just Jensen's inequality, right? The expected value of the norm is less than the square root of the squared expected value, and the expected value of the norm squared, well, that's just the sum of the, because of independence. Okay? In the last equality, we used the fact that the expected value of the norm squared, xi squared, well, this is the sum of the expected values of the individual norm squares plus, for all I, let's say, greater than j, twice the expected value of the inner product of xi and xj. But these are zero mean random variables, and they are independent, so this guy here equals 0. Right? Because remember, we assume that these random variables have zero mean, zero expected value, and they are independent, so the expected value of the inner product equals 0. So this goes away, and this guy here, well, the xi squared, this is less than whatever. Is there a mistake here again? T minus n times c squared. Okay, yes, that's correct. I think it's okay. Yeah, so the norm, the expected value of the norm is bounded by root v. So this guy here is less than. So if I put it here, this guy is less than root v. So I get exactly the same. So this is another very nice application of this type of inequalities. We can go in an infinite dimensional space. We can look at the norm, and it behaves nicely because of the simple fact that the function that we are looking at is simple. All right. So these are some pros and cons of the bounded differences inequality. It's really easy to use, very, very useful. It has a million applications, at least. And it's also very nice because it's distribution free, right? There's nothing here. There's nothing here that depends on the distribution. It only depends on this property of the function. If our function has this property that by changing one variable it cannot change too much, then no matter what the distribution is, these don't even have to have the same distributions. The only thing we need is independence. Okay? So it's distribution free. Again, learning theorists love it. It's very close to optimal in many cases. Recall the example of kernel density estimation. Let me go back here. Remember when we looked at NIID samples drawn from a density function, and we estimate this density function using the kernel density estimate, and then we looked at the L1 error, which is a complicated random variable. But we could prove very easily that this function has the bounded differences property. If I change one point in my sample, then the value of the L1 error can never change by more than 2 divided by n. So back here we use the Efronstein inequality to show that the variance is less than 2 to the n. But now we get something much stronger. We get a sub-Gaussian tail. Right? Here we have the probability that the L1 error differs from its expected value by more than t is less than something like twice e to the minus n times t squared, and I'm not sure what the constant here is. It's probably 2. Okay? So we get, for free, again, just using the bounded differences inequality for this complicated random variable, we have sub-Gaussian tail bounds. Right? This is much stronger than what we had here. Both inequalities tells us the typical variations are of the order of, typical deviations are of the order of 1 over square root of n. Right? Here, if t is of the order of, if much bigger than 1 over root n, then this is already small. But this decreases much faster than what we get from the variance. Okay? So and this is close to optimal in this case. So in many cases, this is we get sharp results. On the negative side, this is inequality just recovers Hubbs's inequality. It doesn't recover Bernstein's inequality. So sometimes we want to say something more. So maybe we know that the variance of these guys is maybe much smaller. So again, because the inequality is distribution free, for many distributions it won't be optimal. Okay? So and this inequality doesn't take variance information into account. And it's a little bit too rigid because of this. So for example, it doesn't allow us to handle self-bounding functions. Right? Because it only tells us something like, if the function cannot change by more than, let's say, 1, then the typical deviations are of the order of root n. That's all it says. It doesn't allow us to say more. So in order to say more, some other methods are necessary. And these other methods is what I'm going to talk about. Okay? And now I will have to go back to 1948 and just give you the very, very basic definitions of entropy. Are you all familiar with basic information theory? Yes? Okay, so but anyways, it's just one slide or 2 slides that we need from information theory. It's very, very basic things. So if we have discrete random variables, let's say they take values in a set of size capital N, then the entropy, the Shannon entropy of this random variable is defined like this. It's minus the expected value of the log of the probabilities. Okay? So minus p log p. Okay? Summed over all possible capital N values. So this sum is for all possible values that the random variable can take. Okay? Now if you use Jensen's inequality, then it's very easy to see that this, well, first of all, it's clearly because p is between 0 and 1, clearly this is a non-negative quantity. And by Jensen's inequality, this is always less than log n, the log number of possible values that the random variable can take. And we can also define the so-called conditional entropy, which is, we look at the entropy of the pair xy. Right? Now this xy pair can take n squared possible values, but it's still a discrete random variable, so we can define this joint entropy exactly the same way. And we look at the joint entropy minus the entropy of y. That's the so-called conditional entropy of x given y. If you write it out, this is what you get. Okay? And again, by Jensen's inequality, you can prove that the conditional entropy can never exceed the original entropy. Okay? So there's an easy way to remember these inequalities by by giving an intuitive interpretation to entropy, the entropy is somehow the uncertainty of a random variable. Right? That's how we like to think about this. It's a helpful way of thinking about it. So the maximum uncertainty, this equality here is achieved if x has the uniform distribution. Okay? So that's somehow the most uncertain. The outcome is the most uncertain for if the distribution is uniform. Okay? And the conditional entropy has the meaning of that if someone tells us y, then how much do we know about x? Okay? That's the conditional entropy. And by conditioning, our uncertainty about the value of x can only decrease. So that's a useful way of remembering this. In fact, you can show that you have equality here if and only if x and y are independent random variables. So in other words, if x and y are independent, then knowing y doesn't help us, doesn't give us any information about x. Okay? So our uncertainty does not decrease in that case. But if they are dependent, then we learn something about x if the value of y is revealed. Okay? So this is all we need about information. All right? Okay. Maybe I show you this little inequality that's called Hans inequality, which will be very useful for us. So take now a vector of random variables, but these don't have to be independent. Okay? Let's just suppose that they take values in a finite set so that everything is well defined, but this can be extended. Okay, so take a vector of n random variables, not necessarily independent again. Okay, I want to emphasize this. And now take xi is the vector when I leave out one of the guys. Okay. Now Hans inequality tells us that if I look at by how much the entropy changes if I leave out one guy, well, the entropy can only decrease, okay? And I look at the sum, then the sum of these differences is always less than the entropy of the original random variable. Formally, this looks like our self-bounding property. Okay? A little bit. And in fact, there's a connection there. Okay? So this is Hans inequality, and the proof is these two lines. So let me show you. So the entropy of x can be written. Well, I can write x as the vector of xi and x sub I. Okay? This is a pair. X is a pair of xi and the rest of the variables. And now this was just the definition of the conditional entropy. This is the definition of the conditional entropy. Conditional entropy equals the joint entropy minus the entropy that's in the conditioning. So that's what's written here. The conditional entropy equals the joint minus what's in the conditioning. Okay? And now I use the fact that conditioning, the second fact. Oops. I will use this inequality, that by conditioning I can only decrease the value of the entropy. Okay? So this means that if I here take less variables in the condition, right, x superscript I is everything, x1, xi minus 1, and the rest of the variables. So now if I scratch the rest of the variables, I take less guys in the conditioning, then this conditional entropy can only increase. Okay? So I'm using actually this inequality conditionally. So we have this inequality here. And now we use the so-called chain rule. So I sum both sides of this inequality. On one side I get the sum of hx. On the other side I get the sum of the xi's. So I have this difference. And this difference is less than the sum of these guys. But what's the sum of these guys? Well, that's just a joint entropy. It's again, this is just the definition of conditional entropy. Because the entropy of x1 and x2 that I can write as the entropy of x1 plus the entropy of x1 given x2. Sorry, x2 given x1. Right? And now I can recurse the entropy of x1, x2, and x3 equals the entropy of x1 plus the conditional entropy of x2 and 3 given x1. And then I can just, and what we get is this inequality, right? If we unfold it. Okay? So the entropy can be written as the sum of these conditional entropies, and that's how we get it. Okay? So that means that the sum of these guys is just one more of the h-axis, which I take up to the other side, and this is what we get, which is equivalent. Okay? So this is Hans inequality, and we will see that the Hans inequality will give us an analog of Efron-Stein inequality, which will be tremendously useful for deriving exponential concentration inequalities for general functions of independent random variables. This is the basic idea. It's a very, very simple entropy argument, and we will see that this will lead us very, very far. But maybe we can take 10 minutes now.